One of the most important things we can do in machine learning is figure out which features to extract from our data to send to our model for training and ultimately inference. Many modern deep learning techniques do allow us to send raw data right to the model and have the model figure out which features it cares about. But that often requires a lot more processing power than we have available in some of our embedded systems. At this point, you may be wondering, what is a feature? For machine learning, a feature is an individual measurable property or characteristic of a phenomenon being observed. Let's start with a simple example. Here is a plot of one of our 10-second motion examples we gathered earlier. By looking at it, can you tell which motion it is? I'll give you a hint. Look at the legend to see what's moving, the X, Y, or Z axis. This is the left to right motion, as the x-axis plot tells us it was moving back and forth. Now, let's start by looking at a very simple example of a feature set. We'll take a single point in time and look at the x, y, and z acceleration data at that point. We could potentially use this as a simple feature set. Each value in the feature set makes up a dimension in the input to our machine learning model. So we'd say that this feature set has 3 dimensions. Our machine learning model would then always expect 3 inputs. We would use these features and associated labels to train the model. When it's done training, the model would once again look for 3 features as inputs and use those 3 features to try to predict the class that they belong to. Do you think that these features make for a good feature set for our model to predict these particular motions? Why or why not? These are actually pretty poor features because they do not take a time sequence into account. It's just a snapshot in time of what the accelerometer is seeing. The input to the model is just this snapshot. There's no information in these features about how the acceleration changes over time. The nice thing about 3 dimensions is that we can plot that point pretty easily and visualize what's going on. Now, let's plot similar points taken from different samples from each of our 4 classes. I've made each of the classes a different color. It's a little messy, but you can see that there are distinct shapes. Most of the time with classification problems in machine learning, if you can visually separate the clusters of samples, you can train a machine to do the same. However, if you look at the center of the group, you can see that all of the samples merge together in one clump. This is where the x, y, and z acceleration in each of the 4 motions looks about the same. So there are some snapshots in time where all of the classes look about the same, and the machine learning model will have a hard time discerning the difference among them. One way to fix this is to use the points in a longer window of time as inputs. Let's make our window long enough to capture 1 or 2 cycles of the movement, which would be about 2 seconds in each axis. With a sampling rate of 62.5 Hertz, that gives us 125 samples for each axis. So in total, that's 375 data points being fed into the machine learning model. Unfortunately, this means our input matrix to the model is now 375 dimensions, which is much harder for humans to visualize. Many machine learning models, like deep neural networks, are capable of extracting the necessary features from large inputs like this automatically. They can take large input arrays and learn what to look for to make good decisions. However, there are 2 main problems with this approach. Here is an example of a deep learning model. We'll see something like this when we explore convolutional neural networks later in the course. These networks can take images, which consists of hundreds or thousands of pixels corresponding to hundreds or thousands of dimensions, figure out what features to look for in those images, and then classify the image based on those features. The problem is that as the machine learning model grows in size and complexity, so do the computational requirements. It takes a lot of processing power to automatically learn what features are useful for the classifier and then use that feature extractor in real time. With a 1000 dimension input, you're going to need to store at least that amount of data in memory and be able to perform mathematical operations on each of those values. Feature extraction sections in such a model can often be several layers deep, multiplying the computational complexity required to perform inference. Additionally, as we make machine learning models larger, they generally require a lot more data to train. Often, we don't have an endless supply of training data and an endless amount of time for training. While such deep learning models may be great for huge server farms doing things like natural language processing, we don't have that luxury in embedded systems. Even though we can and will use deep neural networks in this class, you will benefit greatly by choosing appropriate features from the raw data. You ultimately want to keep your machine learning model as small and fast as possible, as most machine learning algorithms require a lot of memory and processing power, and those are in limited supply in most embedded systems. One way we can do this is by choosing the features for the model manually. Rather than picking and choosing some of the raw samples, we can combine the samples in a variety of ways to generate unique features that help describe what's going on in the system. For example, maybe we calculate the root mean square for all 125 samples in each axis. This is a straightforward calculation that gives us a single number per axis and gives us something like an average or mean for all these numbers in each axis. We're back to having only 3 dimensions as the input for our model, and they take into account 2 seconds of data. One thing you might want to do is filter out the mean of each set of data before calculating the root mean square so that gravity is taken out of the equation. In fact, this is exactly what Edge Impulse has done. We could probably create a classifier model that works very well on just RMS data, as there is a lot of separation between these feature groups. But we can take this a step further. One common technique when looking at vibration or motion data is to take the Fourier transform of that data to get information about it in the frequency domain. We won't go into detail about how to calculate the Fourier transform, but know that it's a way to break apart a signal into its various frequency components. The fast Fourier transform, or FFT, is optimized for discrete sampled data like what we have here. This is an example of the left to right motion. If you look closely at the repeating left to right plot on the top graph, you can see that it takes about 1 second to complete one cycle. That means it has a frequency of 1 Hz. Because this is a prominent feature, it will stand out in the frequency domain. Take a look at the bottom graph and you'll see a peak at 1 Hz, noting that there is a large 1 Hz component. Similarly, if you were to move the phone back and forth faster at, say, 3 Hz, this peak would then be at 3 Hz. Edge Impulse takes this even another step further and computes the power spectral density, or PSD, from the FFT. The FFT can be somewhat misleading sometimes, as the amplitude of the FFT in each bin can vary based on the frequency width of that bin. The PSD helps by normalizing the amplitude to the width of each bin. Rather than feed all of the values in the PSD to the model, Edge Impulse extracts a few important characteristics from it. The first is identifying the amplitude and frequency location of the highest peaks of each axis. The second is they sum all of the values between certain ranges in the PSD. These 2 actions help describe the shape of the PSD without needing to use all the values in it, which would require a higher dimension input to the model, and we want to avoid that. If you didn't catch all of that, don't worry too much about it. Just know that the power spectral density is another good set of features, especially when it comes to motion and vibration data. I'll make sure that there is a good article in the recommended reading section if you'd like to dig deeper into the power spectral density. Edge Impulse is taking 375 raw samples from our 2-second window and computing a number of features. From each axis, we'll send the RMS value, 3 peak amplitudes from the PSD, 3 peak frequency locations from the PSD, and 4 summed bins from the PSD to the model. So rather than have a 375-dimensional input to our model, we have a 33-dimensional input, which is much better. You can order the features however you wish, but you should stick to that order throughout the training process and use that same order when you deploy the model for inference. At this point, our feature extraction methods work with 2 seconds of captured accelerometer data. We could simply divide up our 10-second samples into 2-second chunks, but we can actually get more training samples out of each 10-second recording. To do that, we slide the 2-second window over by a small amount. In edge impulse, this defaults to an 80 millisecond increase. This gives us similar but not quite the same raw input values. This is known as a sliding window, and it allows us to multiply the usefulness of the 10-second samples we collected. However, when we go to deploy the model on our embedded system, we will not need to use a sliding window. As you will see, the embedded system will collect data for 2 seconds, then compute features, and then feed those features to our trained classifier. We'll talk about that more in an upcoming lecture.